Okay, so I try to convince you that maybe some of our curves in math can be approximated with polynomials. Okay? They're not really polynomials, they're kind of like infinitely long polynomials. But look at this very familiar problem. You've seen this 1,000 times. We have a1 plus a1 times r plus a1 times r squared plus a1 times r cubed. That is a geometric series, right? Look familiar? Okay? The nth term is a1 times r to the n minus 1. We know that if r is less than 1, it all converges beautifully to this right here. Nothing more, nothing less. a1 over 1 minus r, right? So if r is less than 1, a series like 5, comma 5 thirds, or 5 plus 5 thirds plus 5 ninths plus 5 27ths is going to converge to 5 over 1 minus a third. Okay, so we've done this many times. What we maybe didn't realize was that this is a very profound stepping stone into a much deeper branch of math. Okay, so let's take a look at how we might write this as a sigma real quick. So notice every term on the left has an a1, right? And then there's an r to a certain power. Notice that the powers on the r go 0, 1, 2, 3, etc. In fact, since these represent the first, second, third, fourth, etc. terms, you can see that the power on the n is on the r is actually just n minus 1. So this is just an old rule that you've already known. It equals a1 over 1 minus r if we go all the way to infinity, right? Okay, now what would happen if we let a1 be specifically 1? In other words, what if we start out with a geometric whose first term is actually 1? So let's see what happens there. Okay, so we're saying that this is a1 times r to the n minus 1. If we let the first term be a1, it's going to look like this. 1 times r to the n minus 1. And let's go ahead and let r be x. So this is exactly the same thing as a1 times r to the n minus 1. I just wrote it as 1 times x to the n minus 1. Okay. Now you guys know from your work with sigmas back in pre-calc, or at least algebra 2. Let's say the teacher gave you this problem. N equals 1 to 5 n. Right? What does this mean? This means you plug in 1, you plug in 2, you plug in 3, you plug in 4, you plug in 5, you add it all up. Right? And then sometimes the teacher gives you a problem where it starts at 0 at the bottom, right? Notice that this is the exact same problem. 1 plus 2 plus 3 plus 4 plus 5. Isn't it the same exact problem? What's the difference between the way problems look? Well, this one starts at n equals 1, and the sum n is just n. So it goes 1, 2, 3, 4, 5. This one starts at n equals 0, but the sum n is n plus 1. So this, again, becomes 0 plus 1, 0 plus 2, or 0 plus 1, 1 plus 1, etc. It's still the same exact problem. This is the same problem as the blue one, isn't it? It's exactly the same problem. So if you decrease your limits of summation by 1, let's say, so you make this a 0, make that a 4, the price you pay is you change the n's by increasing them. Okay? So by changing the 5 to a 4 and the 1 to a 0, the price I have to pay for that is to increase my n by 1. The same is true here. Most of our series from now on, we're going to start at 0. So we're going to go ahead and adjust this. I'm going to take away 1 from here. That makes a 0 on the bottom. I'll take away 1 from infinity. Nothing happens. And then what would happen here? I'd have to add 1, wouldn't I, to compensate? So it's going to be 1 times x to the what? N. Okay? So this is exactly the same thing as the previous line. This is exactly the same. But we typically memorize it this way, where this starts at 0. So you're going to see that we're just going to plot as n equals 0s from here on out. All right, so everybody wrote that down? If you sleep through power series, you are not going to pass the BC test. So I'm just letting you know now. Okay. That is a fact you want to memorize, the thing I just boxed. So I'll rewrite it one more time. It's right here. Okay, so this is a very important fact. What is it saying exactly? It's just basically saying that 1 over 1 minus x can be written as an infinitely long polynomial, and I use that word loosely. It's really a series, but look, it looks like a polynomial. 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth plus blah blah blah. Okay? Now this is only valid if r is less than 1. In other words, if x is less than 1. Okay? So I showed you just a moment ago the graphs of 1 over 1 minus x and the graph of 1 plus x squared plus x cubed plus x to the third plus, or x to the fourth, all the way up to 7 actually. So just for those who aren't here today, I'll show the picture here. The red here is 1 over 1 minus x, and the blue is not everything, but it's from 0 to 7 at least, x to the n. It's basically 1 plus x squared plus x to the third plus x to the fourth plus x to the fifth plus x to the sixth plus x to the seventh is what it is what you're looking at. And notice the nice tight fit they have on the interval between -1 and +1. So the blue and the red concur pretty well in this interval only. If you go outside this interval, they diverge apart from each other. Okay? All right. So you can graph them on your calculator too if you want, even though I kind of already did. So I might not fill in every blank on this handout, since I already kind of showed you everything there. But you could write something like, for x's between -1 and 1, 1 over 1 minus x is very similar to 1 plus x squared plus x cubed plus x to the fourth. This is the first 5 terms. Okay? So you can kind of freehand draw this if you want. You guys have a little graph paper there. Let's just draw it in. This is 1 over 1 minus x. Then there's this asymptote here. If you're anywhere between -1 and +1, which is where this asymptote is, 1 plus x squared plus x cubed plus x to the fourth, the first 5 terms looks like a quartic, actually. Watch this. Looks like a 4th power function, and it fits real nicely up against that red. Even better than I've drawn, really. Okay. All right. This becomes a stepping stone. So you guys have to memorize this formula. Okay, you don't have to memorize everything on this page, but you have to memorize this one. I'm writing it one more time in green. You've got to know that guy. I wrote that wrong. Make sure you write it right. It's 1 over 1 minus x. And you got to know that it's only true only if you're between -1 and 1 for x. Okay, so don't use this for all x's, but you can use it for numbers between -1 and 1. Okay, everybody got the green formula? That's the takeaway from this page. It's the only takeaway you have to have. Okay? It just comes from the geometric series formula. Okay, so in the previous activity, we just kind of had one simple takeaway. And it's actually right here. Okay, so this is where we left off. And what I'd like to do is to see if 1 over 1 minus x, which looks kind of like this, can be approximated using power series, that means like a polynomial type thing, for the interval between negative 1 and 1, then I wonder if other functions can be treated the same way. Can we approximate other types of curves using this series idea? Okay, so we're just going to kind of goof around with this. We're going to change each x in this problem, and there are 3 of them, to a 1 minus x. Let's see what happens. So we get 1 over 1 minus x equals sigma n equals 0 to infinity 1 minus x to the n for negative 1 is less than 1 minus x less than 1. Let's play around with this for a minute before we fill in any more blanks. This is now simply 1 over x right here. This is just, let's write this as negative 1 times x minus 1 all to the n. And let's pursue that a little bit more. Okay, so this is 1 over x equals n equals 0 to infinity, negative 1 to the n, x minus 1 to the n. There we go. Let's talk about this part over here. Let's take away 1 here, here, and here, and we get this statement. Negative 2 is less than negative x is less than 0. If we divide by negative 1, here, 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 what do we get? We get 0 is less than x is less than 2. Notice the inequality flipped around. So this is a little bit more profound than what we said before. This is saying that the function 1 over x, which is quite familiar to us, can be written this way. So let's go ahead and put our conclusion down. 1 over x can be written as sigma n equals 0 to infinity, negative 1 to the n, x minus 1 to the n. And let's just go ahead and change this to 0 is less than x is less than 2. All right, now, okay, so why would I have you do that? Well, 1 over x is a pretty familiar function. Now let's take the antiderivative. Watch this. If we integrate 1 over x, we get ln x. I would put an absolute value here because you're supposed to do ln absolute value x, but we're dealing with x's specifically between 0 and 2, so I don't feel it's really necessary. And let's find the antiderivative of this series. Can you take an antiderivative of a series? Sure you can. There's nothing wrong with integrating a series. Let me show you why. If you want to integrate this series, what you're really doing is integrating an infinite number of polynomial-like terms. Okay? So because this is kind of like a polynomial, you could go through it term by term and anti-differentiate each one. Then you would try to recreate a sigma. Well, guess what you're going to get? Watch this. What's going to end up happening is all your powers will go up by 1. So now you're going to have an x minus 1 to the n plus 1. It's 1 power larger. You're going to find yourself dividing a lot, specifically by the new power on every single term. As for the negative 1 to the n that was in the original problem, it's like a coefficient and it doesn't change at all. Okay, so this is just 1 power larger than the black sigma above it, and it's got that new power on the bottom, so it's the antiderivative. The negative 1 at the end just stays there. It's like a coefficient of integration. Remember, we're integrating with respect to x, so don't worry about n. Let's write out the first few terms of this series to get the hang of it. So we're saying that ln x, and let's go ahead and write out 5 terms. ln x is basically this. It's negative 1 to the first times x minus 1, negative 1 to the 0, which is really just 1. So we're going to plug in 0 first on these. See the lower limit of summation? So you plug in 0 first. You're just going to get x minus 1 over 1, basically. So you're going to get x minus 1. If you plug in 1, you're going to get a negative, and there's going to be a 1/2 x minus 1 squared type look. Okay? Then the next term is going to go back to being positive. It's going to be 1/3 x minus 1 cubed, followed by 1/4 negative 1/4 actually. And it'll be x minus 1 to the 4th, and then it'll go back to positive and so forth. And this goes on literally forever. Let's say you wanted to find ln of 1.5, but you didn't bring your graphing calculator to class or something. So you would just basically do 1.5 minus 1 minus 1/2 of 1.5 minus 1 squared plus 1/3 of 1.5 minus 1 cubed. Then you go back to minus 1/4 of 1.5 minus 1 to the 4th, you see. Let's do one more for good measure. Haha, get it? Better measurements, more terms. This is not exactly ln 1.5, but it is close. Let's see how close we got. Alright, so first let's go ahead and find ln of 1.5. Okay, so here we go. 0.40546, yada yada. Okay, now let's go ahead and try our power series. So it's supposed to be 0.5 minus 0.5 squared over 2 plus 0.5 cubed over 3 minus 0.5 to the 4th over 4 plus 0.5 to the 5th over 5, you see. Look at that, 0.40729. 0.40729. So what is my error? If you subtract off ln 1.5, you can see we are within 2/1000th of the correct answer. Our absolute error here is only 0.0018. Pretty accurate for considering the fact we only used one term or 5 terms here. Okay? All right. Now if you just include the first terms, those aren't very accurate, right? Like if you just do x minus 1, that's just the line right here. X minus 1 looks like this line. That doesn't look anything like the red curve. But if you go ahead and use x minus 1 plus 1/2 of, or excuse me, minus 1/2 of x minus 1 squared, that now is a polynomial that fits this better, you see. Doesn't look much like a polynomial. It's a parabola, I should say. It's got to look like it fits a little bit better there. And then the third case is, you know, x minus 1, and then minus 1/2 x minus 1 squared, and then plus 1/3 x minus 1 cubed. And that thing's a cubic, and that cubic fits even better to the curve ln x. Interesting concept of the day. And that's our first day of power series. We have 2 takeaways. Let me write them down for you in green. Besides conceptual takeaways, like a curve can be written as a series of polynomial terms, the specific takeaways we want today are this one. This particular series is a replacement for 1 over 1 minus x. And this little more complicated version, negative 1 to the n, x minus 1 to the n plus 1, all over n plus 1. This is a replacement for ln x. Whenever you memorize a formula like this, memorize the interval of convergence. That just means go ahead and memorize for what x is it's true. This is only true for x's between negative 1 and 1. This is only true for x's between 0 and 2. We call this the interval of convergence. And if you look at what is half of the interval of convergence, so notice that this converges between -1 and 1. Notice that total distance there is 2, right? So we would say that the radius of convergence is 1. So we'll talk more about radius of convergence later, but r equals 1 means, since this interval is 2 units long, half of that is 1. We call that the interval of convergence. Oh, sorry, radius of convergence. So r is 1 on this, and on this next one too, the radius is 1. Because from 0 to 2, you have basically 2 units again. So it looks like this. And so this would be like a shading of the region of convergence. And then half of that would be r equals 1. So we'll talk about radius later. But these are your takeaways, the 2 greens, and the red domain rules that accord them, that go with them. All right? That's it for today.